Hello students, myself Mohammad Hussein. In previous lecture we have seen about the Laplace transform of some functions. Now today we will learn some more examples on the basis of Laplace transform, in which we are studying about the Laplace transform of function, Laplace transform of function f of t having denominator t or that is f of t upon. Today we are going to find the Laplace transform of function in which the function is divided by t, and we have already seen the theorem about how to solve the function, how to find the Laplace transform of function which have division with t, and the statement of that theorem is Laplace transform of f of t divided by t is equal to integration from u to infinity f of u dt, where capital F denotes the Laplace transform of f of t. Correct? We are going to study or we are going to solve example which are of the following phase. If such type of phase appear of the function and examiner or anyone asks to find the Laplace transform of such function, then we will use the theorem in which we have studied about that the Laplace transform of f of t upon t is equal to integration from u to infinity f of u du, where capital F of u denotes the Laplace transform of f of t. Means what we have to do here, we have to find Laplace transform of f of t first. Correct? First of all, find Laplace transform of f of t and then integrate in between u to infinity with respect to u and convert this f of t, Laplace transform of f of t in the form of u and integrate. So take example number 1, find the Laplace transform of find the Laplace transform of sine 2t upon t. Correct? Here we have given a function sine 2t and which is divided by t, means we are getting such type of example to solve here. So first of all, find f of u, means what is mean by f of u? F of u is the Laplace transform of f of t in the variable of u. So find Laplace transform of sine 2t. Since we know that Laplace transform of sine at is equal to a upon s square plus a square. We already know that Laplace transform of sine at is equal to a upon s square plus a square. Now we are going to find Laplace transform of sine 2t. Then we will get here sine 2t, and if we equate this with sine 80, we will get 2 is equal to a. Correct? And the formula says a upon s square plus a square. So we will get 2 upon s square plus b square, and which is equal to 2 upon s square plus 4. Correct? We have given to find the Laplace transform of sin 2t upon t, and we know that the formula Laplace transform of f of t upon t is equals to integration from u to infinity f of u du. For our convenience, we can replace this u by s also. So we can write the limit of this integration as s to infinity f of u du. Correct? And we have calculated the first Laplace transform of the numerator, that is sin 2t, and we will get 2 upon s square plus a square, means 2 upon s square plus 4, and it is Laplace transform of sin 2t. Correct? Now put this value in this theorem's statement, that f of t upon t is equals to s to infinity integration from s to infinity. Replace s by u, since we want f of u, so we will get 2 upon u square plus 4 d. As per our statement of the theorem say, we have converted this Laplace transform of f of t into u variable, and we get the integration from s to infinity 2 upon u square plus 4 du. Correct? Now, since 2 is constant number and we can take it outside from limit, and we will get 2 into limit 2 into integration from s to infinity 1 upon x square. For convenience, we can write it as 2 square du. And friends, we already know that the Laplace transform of the integration of 1 upon x square plus a square dx is always equal to 1 upon a tan inverse of x upon a. Correct? It is the formula for integration of 1 upon x square plus a square dx, and we will get 1 upon a tan inverse x upon a. Now we can apply this formula to this example also. For 2, as it is 1 upon a, and here a is 2, so we can write it as 1 upon 2. Correct? Now, taking integration of 1 upon x square plus 2 square, we will get 1 upon a tan inverse x upon a. Then tan inverse x means s and a means 2. Correct? 2 to get cancelled, and we will get tan inverse of x by 2. We will get tan inverse of x by 2, and here we can put the limit of the integration. So putting the limit tan inverse infinity minus tan inverse of pi by 2, tan inverse of s by s. Correct? Now tan inverse x by x becomes tan inverse of 1, and tan inverse of infinity, tan inverse of infinity becomes, here we can write it as u square u upon 2 and s upon 2. Correct? Now tan inverse infinity becomes pi by 2, and tan inverse of x by 2 after putting tan inverse s by 2 which is equals to cot inverse x by 2. Correct? We will get cot inverse x by 2. First of all, we have an example f of t form sin 2t upon t. And the theorem of Laplace transform say Laplace transform of f of t upon t is equals to integration from s to infinity f of u du, where f of u is a Laplace transform of small f of t. So we have calculated the Laplace transform of f of t, or we can say that Laplace transform of sin 2t, and we will get 2 upon s square plus 4, or we can say that 2 upon s square plus 2 square. Correct? Now we have the value of f of u. Correct? But we have to apply only the integration s to infinity in the form with respect to u. So we convert this Laplace transform of sin 2t into u form, and we will get 2 upon u square plus 4 with integration, because we have taken the denominator also with this function, and the theorem said that integration from s to infinity 2 upon u square plus 4 du, and we know that integration of 1 plus s square plus a square dx is equals to 1 upon a tan inverse x upon a. So we will get 2 constant taking outside. We will get integration of 1 upon u square plus 2 square. 1 upon a is 1 upon 2 tan inverse u upon 2, because at the place of x we have u, so u upon a means u upon 2, and limits of integration are infinity to s. Putting the upper integration, we will get tan inverse of infinity minus tan inverse of s by 2, and tan inverse of infinity becomes pi by 2, and minus tan inverse s by 2. Pi by 2 minus tan inverse s by 2 becomes cot inverse s by 2. So it is the first example of our Laplace transform of f of t by t. So dear friends, now second example is Laplace transform of e raised to minus 4t upon sin 3t upon t. Here we will apply two theorems at a time. First of all, we will use Laplace transform of e raised to ADF of t, that is f of t minus a, and Laplace transform of f of t upon t. So here we have one theorem, and we will use another theorem with the solution of this example. So find Laplace transform of sin 3t upon t. We know that we will get integration from s to infinity f of u du, where f of u is the Laplace transform of sin 3t. So find Laplace transform of sin 3t. We will get Laplace transform of sin 3t equals to 3 upon s square plus 3 square. Since we know that Laplace transform of sin at is equals to a upon s square plus a square. Correct? Now Laplace transform of sin 3t upon t becomes integration from s to infinity 3 u square 3 square du. Correct? Taking 3 outside, since 3 is constant, so we will get 3 into integration from s to infinity 1 upon u square plus 3 square du. Correct? We have 3 into integration from s to infinity 1 upon x square u square plus 3 square d, and we know that the tan inverse form integration from 1 upon x square plus a square du is equal to 1 upon a tan inverse of x upon a. It is the integration of 1 upon x square plus a square. So we can take the result from that formula. We will get 3 as it is. Then from this 1 upon a means 1 upon 3, correct? And tan inverse of u upon 3. So we will get 3 get cancelled, and the limit points are s to infinity. Now tan inverse of infinity upon 3 minus tan inverse of s upon 3. And we know that infinity upon any finite number we will get tan inverse of infinity minus tan inverse of s upon 3. So we will get tan inverse of infinity becomes pi by 2, and tan inverse of s by 3 we will get quad inverse of s by 3. Correct? This is Laplace transform of sin 3t upon t, and the result is quad inverse of s by 3. Now the whole example is Laplace transform of e raised to minus 40 sin 3t t. Since we know that Laplace transform of e raised to 80 f of t becomes f of t minus a. So we will get the resultant quad inverse s becomes s minus minus plus 4, s minus 4 upon 3. So we will get quad inverse of s plus 4 by, and s plus 4 by 3. Complete s plus 4 by 3. Correct? We will get, or we can write it as also in the form of tan inverse of 3 upon s plus 4. Both the answer are correct. If you want to stop at this point, you can, and if you want to continue up to tan inverse of 3 by s plus 4, it is also okay for the result. Yeah, it was our second example, and now we will start with third example. And we have the third example as Laplace transform of 1 minus e raised to t upon t. Since we know that the Laplace transform of f of t upon t is equal to integration from s to infinity f of u du, where capital F of u is the Laplace transform of f of t, means Laplace transform of numerator. So let us find the Laplace transform of numerator. We will get, since we know that the Laplace transform of 1 is equal to 1 upon s, and Laplace transform of e raised to t becomes 1 upon s minus 1. Since we know that Laplace transform of e raised to 80 becomes s minus a. So here in the place of a we have 1, so we have get the result 1 upon s minus 1. So we can find Laplace transform of 1 and minus e raised to t. We will get Laplace transform of 1 minus Laplace transform of e raised to t. Laplace transform of 1 is equal to 1 upon s, and Laplace transform of e raised to t is s minus 1. Now, since we know that the Laplace transform of 1 minus e raised to t becomes integration from s to infinity f of u du, and we have found f of u, so we can write it as integration from s to infinity 1 upon s minus 1 upon s minus 1 or u. We have find in the form of u, so we can write it as 1 upon u minus 1 upon u minus 1 du. Correct? Du. So we can write it as integration from s to infinity 1 upon u du minus s to infinity 1 upon u minus 1 du. And we know that the integration of 1 upon u du will get log u and limits of s to infinity, and we will get log of u minus 1 integration from s to infinity. So we will get log of infinity minus log of s minus log of infinity minus 1 minus log of s minus 1. Correct? We have used the limits of the integration which are s and infinity. So from this we will get, it will become 0, we will get Laplace transform of s minus 1. Since this minus, convert this minus into plus, and minus log of s, and we know that log of a minus log of b becomes log of a upon b, so we can write it as log of s minus 1 upon s, and it is the final answer of our this example. Now we will start with the fourth example, which will be start soon. Now our fourth example is, as we see here, Laplace transform of e raised to minus at minus e raised to minus bt upon t. And we know that the Laplace transform of f of t upon t is Laplace transform s to infinity f of u du, and f of u is Laplace transform of this numerator f of t. So first of all we have to find Laplace transform of e raised to minus at minus e raised to minus bt, and we will get Laplace transform of e raised to minus at minus Laplace transform of e raised to minus bt, and we will get 1 upon s plus a minus 1 upon x minus s plus b. Correct? Yes. And after putting this in Laplace transform of e raised to minus at minus e raised to minus bt upon t, we will get integration from s to infinity, and the Laplace transform of this function means 1 upon u plus a minus 1 upon u plus b du, and we can write it as s to infinity du is equal to u plus a minus s to infinity bu upon u plus b. Correct? Now taking u plus v as to infinity. After putting the value infinity, we will get log of infinity plus a minus log of s plus a minus, as it is, log of infinity plus b minus log of s plus b, and we will get, this becomes 0, this becomes 0, we will get minus minus plus, we get log of s plus b minus log of s plus a, and we will get log of s plus b upon s plus a, and it is our final answer, and it is enough to understand the Laplace transform of function in which we have division by t. So we will stop at this point. We will continue with a new example and new type of Laplace transform in next lecture. Till then, thank you. Bye.